In this video, we'll talk about our next technique for integration, which is substitution methods. So this is our, general substitution type method, where if I have a function and its derivative, I can then use a u substitution to give me a way to find the antiderivative. And this is sort of the big thing you're aiming for with these sorts of problems. You're going to see a function and its derivative. You also will want to think about this when you see a composition of functions. When you see one function inside another, we have no way to integrate that right away, but if we can get rid of that part that's inside, make it a u, then we'll be able to integrate the resulting expression. There's also one more way this comes up, and that's the idea of a rationalizing substitution. And we'll do an example about that one in a bit. Here's our first example, x to the 7th times root 1 plus x to the 4th dx. This is one where you're going to have to do some sort of solving out to get this problem to work out. So what you want to do here is make u the inside function. So u is 1 plus x to the 4th, making du 4x cubed dx. This then means this integral becomes an integral of 1/4 x to the 4th square root of u du. And I can then plug in for the x to the 4th using this setup here. This becomes a 1/4 integral of u minus 1 times the square root of u du. And then I can solve out to integrate this out. I can distribute the square root of u, which I can then integrate, and then plug in my u, which is 1 plus x to the 4th, to get that antiderivative. That's what we get for that one there. For the other example, we have this idea of a rationalizing substitution. And the idea here is that I have weird exponents going on here in terms of x. If I could find a way to get rid of those weird exponents and make them all whole number exponents, I might have a better shot at solving this problem. So what I want to do is I want to pick a substitution that turns all of this into whole exponents. So what I want to do is basically find a fractional exponent and use that to make the problem easier. And the way that's going to work is I am going to set here u is going to be x to the 1/12. Why do I do that? I do that because x to the 1/3 is then u to the 4th, and x to the 1/4 is u cubed. That gives me a good shot at trying to figure out how to solve this problem if I make that substitution. With this, though, I have a du, and the du is then 1/12 x to the minus 11 over 12 dx, or 12 x to the 11th over 12 du equals dx, but since u is x to the 1/12, this is 12 u to the 11th du is dx. So now I can plug this in and see what I would get. If I plug in this substitution, I will see the following. I will see the integral of x to the 1/4 is u cubed over x to the 1/3 is u to the 4th minus 16, and then times a 12 u to the 11th du, which gives me an integral of u to the 14th over u to the 4th minus 16 du with a 12 out front. Now how would we go about solving this integral? Well, this is a rational function, but the top has a higher degree than the bottom, so we'll have to do long division first and then go into partial fractions. Right, this bottom will factor as a u squared plus 4 times u squared minus 4, difference of two squares, and I can do that again on the next term. U squared plus 4 times u plus 2 u minus 2. So that gives me my way to do my decomposition, but I have to get this exponent down lower first. So you need to do long division to get that down lower. You then have a polynomial, and you'd have the remainder term, which would be done by partial fractions. I'm not going to work that one out in full detail here, but you can see how that would work based on our partial fractions technique from before. So here's the idea of substitution. You really have two types. The one you would know and been doing for weeks at this point before, which is your standard u substitution problem. And you have this one where you're going to try to rationalize all your exponents by picking an appropriate power for u that makes it so everything turns into a whole number power of u, and then lets you solve it by another method that we've learned before. So these are the main ways substitution comes up when you're trying to solve these sorts of integration problems. When you're looking at a generic problem and saying, can I use substitution to solve this? These are things you want to think about going into those problems.